we'll talk about motion in 2 dimension. And good example for that is projectile motion. We all have studied projectile motion before, or at least we have heard about. When I throw this to what's your name? To Hassan, look at the motion. Tell me what does it change. Will the x position of the object change? Will the y position of the object change, or will the z position of the object change? Which one of them will change? This is a projectile motion. What did it change? Did the x position change? Yes. Did the y position change? Yes. How about the z position? No, it did not change. Remember, for the people who it doesn't matter. You know, I can say this is x and this is y, and I can say this is x and this is y. So it doesn't matter. We're flexible in that. Yeah, I'm free to say whatever I want. You're free to choose your coordinate system the way you want. I can say that this is x and this is z. And of course this is going to be y in that case. Someone else will say, no, this is y, this is z, and this is going to be x in that case. So you're free to do whatever you want as long as you tell me what are you doing. As long as you put a little map telling us which coordinate set did you choose and what are, and you label it. If you label it, then that's fine with us. Multiplying 2 vectors. Yes, we're going to study. You'll find it in chapter 3, cross product and dot product of 2 vectors. I can teach it for you now, but we're not going to use it. I postpone it till we need it. We will need it later on in chapter 7, for example. Then we're going to study it. That's why I go a little bit different than the book, but we're going to cover everything in the book. Going back to the problem that we have, we were talking about, that's motion in 2 dimension, projectile motion. When I throw this to Hassan, you said, guys, this position change, which said that x changed, and this changed. We said that y also changed. But if I go that way, Hassan catch, and I'll throw it to Hassan again. What did it change? Well, did x change? Yes. Did y change? Did z change? Yes. This is a motion in 3 dimension. It's complicated. If we can deal with a motion in 1 dimension, this is easy. Motion in 2 dimension is going to be a little bit hard, but motion in 3 dimension, it's going to be even harder. Can we simplify motion in 3 dimension?
Yes.
How?
Breaking them into 2 kinds of motion.
How?
Two-dimensional.
So, what's your name? Ali is saying, well, can we break it into a motion in 2 dimension? A problem that has a motion in 2 dimension, and a problem that has a motion in 1 dimension? Yes, but that does not really simplify it. We still have the same thing. We have a motion in 3 dimension. Yes. Oh, thank you so much. Going back to your question again, he said, since I can choose my coordinate system the way I want, then this is going to be my x-axis, and this is going to be my y-axis, or z-axis, doesn't matter. This is x, and this is y. Okay? Instead of choosing this is x, and this is y, I'm going to just turn a little bit. I will say this is my x-axis, and this is my y-axis. According to my new coordinate system that you have suggested a minute ago, what does it change? X and y. Now we have converted smartly a motion in 3 dimension into a motion only in 2 dimension by just choosing the right coordinate system. And can we do that? Yes. You can do whatever you want as long as you tell me or you tell us what are you doing. And I mean by that by specifying your coordinate system.
The only condition doing that is to mention that coordinate?
Excuse me?
The only condition for doing that, only that two dimensions?
Yes, you choose the correct coordinate system. So again, Hassan, can I get that back? So now, what's your name? Mustafa, catch. Guys, this is a motion, again, in 3 dimension according to this coordinate system. This is the origin, X, Z, and Y. Now, when I have thrown this to Hassan, Mustafa, now we have a motion in 3 dimension, and we can simplify that by choosing this to be the x-axis and this to be the y-axis. Now we have, again, motion in 2 dimension. So now we know that if we have a motion in 3 dimension, we can simplify that into a motion in 2 dimension by smartly choosing the right coordinate system. That's done. That's easy. Now, going backward. You did not teach us how to solve a problem in 2 dimension. This is very simple. Going back, what's your name? To what Ali said. Now, we should separate it into motion along the x-axis and a motion along the y-axis and deal with them as separate equations, x and y's, using the kinematic equation that we have studied before, and that's it. So we can simplify actually motion in 2 dimension by converting the problem into a motion and actually into 2 motions in 1 dimension and treat each of them separately. You get the correct, then you can get the answer. This is it. This is everything in chapter 4. That's it. The whole physics behind it. From now on, today and Saturday, we're going to solve the problems. Okay, guys? So what we're going to do is we're going to use the kinematic equation again. If you did not memorize them by now, I'm going to write them down. No, you don't have to. But you know, if you solve many problems, like I do, you're going to memorize them by the end of maybe next week by yourself, without even enforcing yourself to memorize them. And if you do not memorize them, you'll find them in the formula sheet anyway. Okay? Can I say something before I just write it down for now? Since I'm talking about motion in 2 dimensions, then I have to specify this is the velocity along the x-axis will equal to the initial velocity along the x-axis plus the acceleration along the x-axis times the time t. Okay? The x position will equal to the initial x position plus the initial velocity along the x-axis times t plus 1/2 acceleration along the x-axis times t squared. Again, final velocity along the x-axis will equal to initial velocity along the x-axis plus 2a. A is the acceleration along the x-axis times delta x. This is the first set of equations. Since we're talking about motion in 2 dimensions, we'll have another set of equations. That's y equal to v0y plus ay t. We'll have y equal to y0 plus v0y plus 1/2 ay t squared vy squared equal to initial velocity along the y-axis squared plus 2a acceleration along the y-axis times delta. Do I have to do that? No, just knowing one of them and knowing that the motion in 1 dimension, in 1 direction does not depend on the motion in the other one. And I mean by that, we need to actually describe that motion carefully, guys. Mustafa. Catch. look at the motion again. Mustafa, catch. What happened to that motion? I give it an initial velocity. I give it an initial velocity along that direction, which means that that initial velocity has two components, one along x and one along y. So at the beginning, I did that. I give it that particle an initial velocity along that direction. That's v initial. So this is my coordinate system. That's j and that's I. That object moved in that direction, in that way. It took that parabolic shape. It took that parabolic shape. Then it reached Mustafa at the end. I throw it in here, and it reaches Mustafa in here. At the beginning, this is the initial velocity. The initial velocity makes an angle theta in here. Can you find the x component, the x component of the initial velocity? Mariam, I want the x component of the initial velocity. Which one is Mariam? Okay, Mariam, go. The x component of the initial velocity. Again, Mariam, remember this is a vector. Velocity is a vector. Can we resolve that vector into two components? One along x. Initial velocity along the x-axis, and one along y. Can we do that? Knowing the angle, that angle is theta. It's going to be V0 cosine that angle theta. So this part is the initial velocity along the x-axis. How about the initial velocity along the y-axis? Mariam?
Cosine,
V initial.
cosine,
Sine the angle theta. So now we know what does that mean. Right? In the first equation. Right, guys? This is the first fact that we know that so far. When I have thrown this to Mustafa, I give it an initial velocity, and that initial velocity can be broken into two components, one along x and one along y. Good. What else? Look at the motion again. What happened to that velocity? I'll ask it in two different ways. First way, what happened to the velocity along the x-axis? It did not change. It will not change. Theoretically. So, Sharif is saying theoretically. He means if we ignore air resistance, then the velocity along the x-axis will not change. That's what he means. And we're going to ignore the air resistance for now. So the velocity along that direction will never change. Why is that? We did not talk about the force so far. There is no acceleration along the x-axis. So look, guys, there is no acceleration along the x-axis. That's why when I leave that object, its velocity will change only along the y-axis. The velocity along the x-axis does not change. It's zero. It will not move along that direction. It will never move along that direction because there is no acceleration along that direction. The only acceleration we have is the acceleration along the y-axis. So that means that ax will always equal to, that's the second fact that we should know. Acceleration along the x-axis will always be zero. The only acceleration we have is the acceleration due to gravity, g, and it's going to be acting along the negative y-axis. Okay, guys? Okay. Then, what happens to the velocity along the x-axis? It did not change. It will continue moving along the x-axis with the same velocity forever. So that velocity here is the same as the velocity along the x-axis at that point. Same thing. How about the velocity along the y-axis? What happened to the velocity along the y-axis? Look at this. I'm going to fill this along the y only, and I want you to look at it and tell me what happens to it. What happened to the velocity? It decreased till it reached the maximum point, then it becomes 0. Velocity. That's why it stops, then it turns back. Okay? So it decreases till it goes to the maximum height, then it stops, and it turns back. And when it's in its way back, what happens to the velocity? It increases in the negative y-axis. Yes? Yes, same acceleration. The same acceleration act, why did the velocity decrease? Because though the velocity is going up, the direction of the velocity is up, but the gravity, the acceleration is pointing down, so the acceleration is acting against the velocity, so the velocity will decrease. That's in its way up. And its way down, what happened? Now the velocity is in the same direction as the acceleration. Acceleration is pointing down all the time. Gravity is pointing down all the time. Now the velocity is in the same direction as the acceleration, so the velocity will increase. This is the action of the acceleration. Acceleration change the velocity. It might decrease it or it might increase it, yes.
The acceleration is posted downwards and negative upwards?
The acceleration is?
Posted downwards and
That depends on my coordinate system.
I think it's always downwards.
It's always downward. There is no acceleration, acceleration due to gravity is always downward.
Yeah, free fall.
It's a free fall.
That's the problem. Sometimes that is tied with now we velocity going up and then going down.
Yeah, I'm getting there. I'm just trying to explain all the physics behind the problem. I want you to see all the facts. Then I'll teach you how to solve the problem later on. Solving the problem is much, much easier than you think. So what happens? The velocity at that point, v y equal to 0 and vx equal to the initial velocity. It did not change.
You know x time, like for the vy.
Excuse me?
You know x time, like for the vy for يعني for y, it's y and then this is t time.
No. This is x position and this is y position. I did not include the time in the graph at all. This is x position and this is y position. I'm drawing this motion to you. This is x and this y. So what happens to the y? The object moves up till it reaches the maximum, then it goes down again. X is what? The velocity along the x-axis does not change because there is no acceleration along the x-axis. I'll say it again. Think about what I say. What I say. The velocity along the x-axis does not change, and the reason for that we do not have acceleration along the x-axis. That's why the velocity at that point along the x-axis at that point will equal to v0x. The velocity at that point along the x-axis will equal to v0x. The velocity at that point along the x-axis is always the initial velocity along the x-axis. It does not change. Okay? Okay? Yeah. So that's the second fact, that the velocity along the y-axis at the top is equal to 0. At the maximum is equal to 0. So that's everything. Most of the books, most of the people will be interested in what is the maximum height, what is the total range, in every physics book, they will try to prove what is h, maximum height a projectile can reach, and what is the maximum range it can reach. And those two depend on the initial velocity and the angle theta. Okay, guys? So now I will try to find an equation for the maximum height and another equation for the range. And this is not a proof, this is just a problem. Any problem can be solved the same way. So do not memorize those equations, even though they put them in the book, and try, and sometimes the book hints to you that you should memorize those equations. No, do not memorize those equations. Just learn how to solve the problem. So now we know what we do. We know that we need to find the R and H. Okay, I'm just trying to think where to start. That motion, for the object to reach that point, it will take time t. To reach that point, it will take time t, and it will take the same time t to go back to its original height. When I throw this up, it took a time t to reach the maximum height, and it took the same time t to go back. Because, can you give me a why is that? Can you explain to me why did I say that state? It takes a time, let's say 5 seconds to go up, and it takes the same 5 seconds to go down. because same acceleration, same distance, correct. So it has to take the same time. You move with the same acceleration and you move with for the same distance, you have to have the same time. Same thing in here. It takes a time t to go up, and it takes a time t to go down. This is another thing that we should know. Now, we need to find h and r. H, which is y maximum, equal to y at that point. This is y maximum. Equal to, guys, can you tell me an equation? It's y0 plus, y0 plus v0y t ay t squared. So it's going to equal to 0 plus, what is v0y? v0 sine theta. Is it positive or negative? Why is it positive? Because it's going up, and I choose y to be positive along the up direction. Plus 1/2. Sorry, the t, thank you. Plus 1/2. What's the acceleration along the y-axis? Negative g times t squared. Now we know what is the maximum height. If we know what is the time t. Right? Now we need to find an equation for that time t. Well, at that maximum point, what is the what is the velocity? 0 will equal to v0 y plus 1/2 ay 80. What's v0 y? v0 sine theta. This is the velocity along the y, the initial velocity along the y-axis, plus what is the acceleration? Can you solve for t? Yes.
What is the 0 stands for?
Oh, initial. Oh, the velocity at maximum height. The velocity along the y-axis, which is that Vy. It's 0. That's why I wrote it 0. Okay? Can you find T?
Yes. But you don't sign theta.
It's everywhere. It's in the book. You just look at it. So from here we can find that this is T will equal to V naught sine theta over G. Right? Right, guys? Of course, do not even memorize that proof. I'm stating the fact. I'm looking at my problem and I know that I need that H, so I wrote the equation for H. I put whatever I know in that equation. I know the initial velocity along the y-axis. I know what is the acceleration along the y-axis. And when I looked at that equation, I found that I do not have T. I need T. I need that time T. So I looked at the equation again and I said, where can I find that time T? I found out that I know that velocity at that point. I know it. And since I know it, and I know that equation that says that V equal to V0y plus AYT, looking at this equation, I find that if I know this, if I know Vy, V0y and AY, then the only unknown is T, then I can solve for T. And I did solve it for T. I found T. Now I should go back to that equation and replace T by its value. I'm going to write that equation again. I'm going to erase it. T plus half minus G T squared. Now, every time I see T, I put its value. So T, I'm going to replace it by each time I need T, I replace it by its value. Right? And here, I replace it by its value. Okay, guys? So, H will equal to, that's 0, V0 sin theta, V0 sin theta, can I do that? It's V0 sin theta times V0 sin theta, that's V0 squared sin squared theta over G. Right? Right, guys? Yes. Okay. That square, I'm going to get rid of it and I put a square here, here, and here. Look at that G. That G will cancel out with the square in here. And that negative sign, I'm going to put it in here. Look at that equation now. Quantity, a quantity minus its half. X minus half X. So this is going to be H is going to equal to 1/2 V0 squared sine squared theta over G. It's always true if you start from the same height, you end up at that height. Because sometimes I put a hill in here and you hit the hill in here and you think that this is the maximum height where it's not the maximum height. This is true when you start from a point and you end up at the same point. So that's different. But the method that I just followed, it's always true. The rule, it's not always true. That depends on the problem itself. So do not memorize the rule. Know how did we think about the problem. Okay? Okay? So before I take that question in here, that equation says if we know the initial velocity and the angle that you send that object with at the beginning and the gravity, I should be able to know what is the maximum height. That's one. Yes. Half x minus half x. X minus half x. You get half x. Okay? Okay, guys? Now we got h. Guys, can you tell me how to get r? The maximum range, the maximum distance along the x-axis that object will travel. So I'm going to leave that. We'll go to the other side. We need r. And we need r. I listen to all ideas, then we'll discuss them together. So listen to what she says. Say it again. Guys, listen.
I mean, if we get make it like triangle, V note by the maximum point layer Py, and make a bit of triangle, tan theta is
But it's not a triangle. It's a parabolic shape. It's not a triangle. I'm going to write that x equal to x0 plus v0x t plus 1/2 ax t squared. That's the simplest way to do it. Is actually we need x, we need r, which is the distance along the x-axis. Then I should write that equation. Then she said that, and a minute ago we have agreed that acceleration along the x-axis equal to 0. Acceleration along the x-axis does not, the velocity along the x-axis does not change. That means that this acceleration is equal to, it starts from 0. So that's v0x, which is v0 cosine theta. Times t. What's t? T is v0 sine theta over g. Then someone said multiplied by 2. Why multiplied by 2? Because I said that it takes time t to go into here and takes another time t to go to here. So that's time t in that equation. That's the whole time 2t. This is actually 2t. So it's times 2 v0 sine theta over g, and the range will equal to v0 squared, 2v0 squared cosine theta sine theta over g. And it can be simplified to a little bit further. I'm not going to go into that. Because 2 cosine theta sine theta sine 2 theta. But I'm not going to go there. It's not even important. Excuse me? This?
Yes, is this v0y or v0x?
No. Look at this. What was that? That was the beginning. That was here, which is v0y. We started from here. v0y, that's v0 sine theta. So v0 is the initial velocity that you give it to the object. Not its component. It's the initial velocity. The whole magnitude of the initial velocity. Okay? The magnitude of the initial velocity. Now we are able to find R and H. Most of the students spend like an hour memorizing those two equations. No. assuming that this is valid for every case. And they find in the exam that I do this. There's a building, and you're going to give it a velocity v0 with an angle theta, and give you magnitude for that, and give you angle for that. Will it hit the building or not? Of course, if you memorize the equation, that's not going to help you. But if you know the physics, then you will be able to solve that problem. Okay, guys? That's everything in chapter 4. Trust me. It's not hard. All what we should know is the following. Initial velocity should be broken into two components. The velocity along the y-axis at the topmost point is 0. Acceleration along the x-axis is always 0. Acceleration along the y-axis is g, and it's downward. And that's everything we should know. Yes.
Is maximum h is always in the middle of maximum r?
Yes. Yes.
Why can't we use the equations on this problem?
Oh, that's easy. Okay, guys? Did we get that part? Now, I keep forgetting your name. Farida. Farida is saying, how can we solve that? Let's see. Before solving this, I want to show you something that we talked about before. Do you remember I said that if you have an elephant and a feather, and you throw them from the top of a building, they will reach the ground at the same time. So what I have here is a tube that we evacuated it, so we took most of the air out, so it's under vacuum, and we have put a coin, which is heavy, and a piece of cotton that's much lighter than it, together. And I'm going to do this. I'm going to flip it over and see if they reach at the bottom together or not, at the same time or not. If they reach the bottom at the same time, that means that the gravity acts on them by the same way. Both of them will start with the same initial velocity. Both of them will travel the same distance. That means that they have to have the same time. That's the explanation that we talked about a minute ago. They have to have the same time. Again, here it is. I'll do it one more time. One more time. It's almost they reach at the same time. Let's put some air in. To make sure that we're not fooling you guys, you're going to hear the voice, the sound of the air going into the tube. So it was really under vacuum. Now it's under air. There is air in. So we're going to have the air resistance in here. Okay, look at it. Now, if there is air, what happens? Okay, try it one more time. It's clear that these do not reach, these do not travel at the same time because there is air resistance in here. But if there is no air resistance, it doesn't matter how much is the mass of the object. If you have two objects, you leave them to fall under the free fall, under the gravity only, they will reach the ground at the same time. Now back to Farida's question, how can we solve that kind of problem? So Farida, this is what we covered so far. I'm going to go over the slides so you would know what's in the slides. We talked about kinematics. We talked about the motion in 3 dimensions. And we said that in motion in 3 dimensions, oh, sorry. That's very important. Okay, guys, So we say that if you have a motion in 3 dimension, we call that 3D kinematics. So position, velocity, and acceleration should be written in the 3 dimension. That's the position. It has an x component, y component, and z component. Same thing goes for the velocity, and same thing goes for the acceleration. And we say that any this is just a revision of what I said before. Any 3-dimensional equation can be broken into 3 different sets of equations. This is the motion along the x-axis. Those equations describe the motion along the y-axis, and those describe the motion along the z-axis. Those mainly say that the position along x equal x of t. That's an equation that's x as a function of t. The derivative of that equation will give us the velocity. The derivative of the velocity will give us the acceleration. Same goes for the 2 other dimensions. I'll skip that. And we talked about throwing a ball. I throw an object to Mustafa and Hassan, and we talked about explanation on motion into 2 dimensions, and we said that we can actually have motion in 3 dimensions broken down into a motion into 2 dimensions by carefully choosing our coordinate system. So then comes to the question that I just asked a minute ago. If we have this problem, we have a baseball player. He hits his ball into the center field. The ball has its head. The ball head is being hit at 1 meter height. So that it does not start from 0. This is the 0, and you hit it from 1 meter height. And it goes with the initial velocity equal to 36.5 meters per second, with an angle with the horizontal equal to 30 degrees. So the initial velocity is given. The magnitude of the initial velocity is given. The angle that initial velocity makes with the x-axis is also given. And the initial position along the y-axis is also given. That's 1 meter. The center field wall, that wall, is at a distance equal to 113 meters from the ball, and it's at a height equal to 3 meters. What time does the ball reach the fence? At what time will it take the ball to reach that fence? That's what the first question in here. The second, does the player get a home run? Or in other words, if you don't know much about baseball, will it hit the ball or not? Will it hit the wall or not? Will the ball hit the wall or not? That's what I mean by the second question here. So that's exactly a typical exam problem. Will it be in the exam? No. Something similar, new idea. So where to start? Let's get in the exam. When I personally go to any exam, my first goal is not to read what's in the wall, but to score points. So what time does the ball reach the fence? What distance will it travel before reaching the fence? D, 113 meters. That distance, D, 113 meters. So I know that it has to travel a distance equal to x will equal to x0 plus v0 x t plus 1/2 ax t squared. Do we have acceleration along the x-axis? No, this is 0. It starts from the initial position, x equal to 0. That means that x will equal to v0x times t. Now, if I know x, which is the case, I know what is x. It's 113 meters. If I know also v, the initial velocity along the x-axis, this is a very simple problem. It's very straightforward. I can calculate t. Do we know what is the initial velocity along the x-axis? Yes. Resolve that into 2 components. Resolve the 36.5. It's not 36.5. Resolve it into 2 components. A component along the x-axis and a component along the y-axis. The component along the x-axis would be v0 times cosine of that angle. So So it's going to be V0 cosine 30. So x, which is 113, will equal to V0 cosine 30 times t. We know what's V0. It's 36.5. Then we can calculate t. I'll leave that to you. You can get t. That's easy. Second one. Will the... Yes.
Why it's initial
Because he did not talk, he did not tell me anything about it. Then I'm free to choose where is my origin. So I choose that to be my origin, which is x0 equal to 0 and y0 equal to 1. Okay. Does the player get a home run? Will the ball hit the wall? What to do? Wait, Ali, wait. Oh, yeah, at that time. See, he spotted what I was actually leading you to, guys. Ali said, well, it will reach the ball after it travels for that time. So all what we have to do is calculate the height at that time. All what we have to do is to calculate the height at that time. In that case, you cannot use the maximum height equation. It's useless. It doesn't mean anything. Though it's a two-dimensional motion, it's same thing, but I don't need you to use that maximum height equation. So Ali said, well, we know that it's going to reach the wall after it travels a distance equal to 113 along the x-axis, and the time t, which is, did you calculate that? Oh. Did you calculate t, guys? 2? 5.7, right? Okay. This is t. If you're correct, then this is the time t. So it will reach the wall after it travels a distance equal to 113 meters along the x-axis, and the time equal to 3.57. So what else to do? Then, right, I need to find its y position at time equal to 3.57 seconds. So we need to know that y0 equal to 1 meter. The initial velocity along the y-axis equal to v0 sine 30. T equals to A. I mean by A, the acceleration along the y-axis, negative G, negative 9.8, and the negative 9.8 because I have chosen Y to be, up to be positive. So if the acceleration is pointing down, then it has to be negative, times t squared again, and here is the t. Done. So if you know your physics, it will take you 2 minutes to solve that problem. And if you don't, y0 equal 1? Okay, good. But if you don't know your physics, it will take you a longer time to solve it. I forgot your name. Abdurrahman is saying why y0 equal to 1? Because it starts from, the ball is hit 1 meter above the plate. The plate is here, and we hit it 1 meter above the plate. Okay? So the y0 is not 0, it's 1. Yes? Just, it's half a t squared. What else? Yes, Sharif.
Are we going to be dealing with horizontal plane, like if this happens on top?
Why not? Why not? As long as you know the physics, you can deal. This is what you're supposed to know, guys. The physics is easy. We talked about everything. Initial velocity has to be resolved into two components. The velocity along the y-axis at the topmost point is 0. The acceleration along the x-axis is 0. Okay? This is everything. sometimes in the exam, I give you problems saying that now we're on a different planet. That the acceleration is not along that direction, it's along that direction. It's a fancy planet. Which means that acceleration along the x-axis is not zero. It will have a component of that. You resolve the acceleration, you find what is the acceleration along the y-axis, you find what is the acceleration along the x-axis, and you deal with the problem. Okay, guys? Okay? So, yes.
Can I take this with that exception?
Yeah, why not? Why not? Usually this is what you're supposed to do. Choose one of the direction of the motion to be your x-axis. The other one, the perpendicular one, is your y-axis. So if I throw the ball that way, this is x, this is y. If I throw the ball that way, this is x, this is y. This will simplify the problem. Okay? Okay, guys? And
If you solve it by this equation, the answer will be different.
of course, this is not valid at all. Totally different thing. So, sometimes this is Farida. Sometimes people say, okay, he needs, I'm going to use the equation for the range. And they consider that D is the range, but D is not the range. D is not the range. The range means that the object leaves at specific height, it goes back at the same height.
But then I place in 1 to 3, so it's not the same.
Yes, it's not the same height.
But if it's the same height, 1 and 1, I can use
Yeah, of course, you can use that equation for the range. Okay, guys, so that's it for today. I'll see you on Saturday. I'm going to start I know that the bus arrives at 9:10, so I'm going to wait till 9:15 and we'll start the lecture. So please, and this is going to be only an hour and a half, not long.